So over the history of mathematics, we figured out some patterns amongst these polynomials and the types of roots that they have. So most polynomials that we work with have what are called irrational coefficients. That means the numbers in front of all the variables are either whole numbers or they are fractions. So they're not numbers like pi that go on forever and don't stop. They're not square roots that don't simplify. It's either whole numbers or fractions or maybe decimals that stop. Those are the most common polynomials we deal with. What we have found is this. If you end up with a root that is a square root that doesn't simplify, something like square root of 2, or maybe you do the quadratic formula and you get 4 minus square root of 7. Those tend to come in pairs. And it comes from the idea of the quadratic formula with that plus and minus in it. If you have one irrational root, so you end up with a square root in one of your answers that doesn't simplify, then whether it's got a plus or a minus in front of it, the other one will also be a root. These come in pairs. They're called conjugates of one another. A conjugate is the same thing, but the sign in the middle is switched between plus and minus. Again, coming from the quadratic formula, something very similar happens with our imaginary numbers. If a plus bi is a root, or if a minus bi is a root, then so is the other one. What this means is, if you know that one of your roots is, say, 2 minus 3i, as long as your coefficients were rational to start with, you also know another root has to be 2 plus 3i. So you get a lot of information without necessarily having the entire picture. So how does this show up? What are you going to be asked to do? Well, it's this. If I tell you that a polynomial has roots of 4/3, 5, and -3 plus root 6, what other roots do we know there must be, if any? Let's take them one at a time. 4/3 does not have a square root in it, is not imaginary, it doesn't tell us anything. Neither of our theorems apply. 5, that's just a positive whole number. No square root, no imaginary. Neither of our theorems apply. But this one, this does have a square root in it. So according to our irrational root theorem, if -3 plus square root of 6 is a root, then -3 minus square root of 6 must also be another root. So look at that. We figured out another root without even knowing what the equation was. That's pretty impressive. Let's keep going. Second set. If we've got -5, okay, that's a rational whole number, so it doesn't have a root, doesn't have an I in it. We don't know anything else based on that. This next one, this next one does have an I in it. So if -1 minus 3i is a root, according to our complex root theorem, -1 plus 3i must also be another root. And again, we're assuming we're starting with a polynomial that has rational coefficients. Then we're guaranteed that those roots come in pairs like that. For these next two, do a quick pause. I would like you to then unpause when you're ready to check and see if you've got the right roots. Okay, in this case, both of these. So this has the I in it. So -3 minus 3i will also be another root, changing the sign in front of the imaginary part. If square root of 3 is a root, then so also is negative square root of 3, changing the sign in front of the root. So change the sign in front of the I, change the sign in front of the root. And now this last one. Now, again, I hope you paused and did it, because we're going to check our answers here, and I'm willing to bet you may actually have made a mistake. From this one, -3i has to be a root. Okay. That means that positive 3i is also a root. Here, 2 plus root 3 is a root. Therefore, 2 minus root 3 is a root. But I'm not going to list it because it's already there. If these are already both showing up, then we don't have any additional information we can get from it, because changing that to a minus just gives me something that's already in the list. And if it's already in the list, I can't be sure there's another one. The reverse holds true then if you do the same thing with the 2 minus root 3. So don't get too conjugate happy. Make sure you check your list and see if the conjugate is already listed. If so, don't list it again. Okay, well, I want to do now the same thing you did in the earlier part of the lesson, this time just with roots that are slightly more complicated. So first, we got a 3/5, a -1 plus root 5, so we know another root is also -1 minus root 5. So to write a polynomial, we're going to set up our factors. So a 5x minus 3. Now for these two factors, it's going to look messy before it gets less messy. You need to do x minus -1 plus square root of 5. And your next factor is x minus -1 minus square root of 5. Like I said, it's going to look a little nasty before it starts to look a little less nasty. My advice is this: don't try and do too much at once. The very next thing I'm going to do is just distribute this negative sign through those brackets. So x plus 1 minus root 5 and x plus 1 plus root 5. The very next thing that I want to do is multiply those two together, the complicated looking ones together. I'm going to do this over here. And the reason I want to do those two is because there's going to be some magic that happens. When you multiply conjugates, a lot of things end up canceling out to 0. So let's see how this works. So x plus 1 minus square root of 5, x plus 1 plus square root of 5. All right, so what do we have here? X squared, x minus x root 5, x 1 minus root 5, x root 5, root 5, and then square root of 5 times square root of 5 is just 5. Positive times negative is negative, so -5. Here's what I mean by the magic. Minus x root 5 plus x root 5. Minus root 5 plus root 5. No more roots. And that should happen every time, as a matter of fact. So if it doesn't, that means I need you to go back, check your multiplications, see where the error was, so that hopefully you can end up in the right spot. What do we then have? I've got an x squared. I've got a 2x. And then 1 plus -5 is -4. So, hey, this may be the first time in your life that you've actually unquadratic formulaed. We just did the quadratic formula backwards, essentially. If you apply quadratic formula to this trinomial, you're going to end up with -1 plus root 5 and -1 minus root 5. Okay, to finish up then, one more multiplication. I'm going to set up a second chart. So 5x minus 3, x squared plus 2x minus 4. So 5x to the third, 10x squared minus 20x minus 3x squared minus 6x plus 12. Okay, so what do we have in the end? 5x to the third. 10x squared minus 3x squared would be plus 7x squared. Negative 20x minus 6x is minus 26x. And then with a plus 12 on the back. Okay, well, it wasn't easy, but keep your work organized and you're going to be okay. So first, use your theorem to find any roots that aren't already listed. Set up your factors, distribute your negative sign, and then start multiplying the nasty stuff first so that then you get a nicer multiplication to finish up. Okay, I'm going to move all of you just over here out of the way so that we can take a look at this next one. Okay, same deal. Start off by making sure you know all the roots you're going to need to know. So -1, 3 plus I. Ooh, this means that also 3 minus I needs to be a root as well. Set up your factors. Once again, they're going to look a little nasty before they start to look neater. So x minus 3 plus I is x minus 3 minus I. The way you may have noticed that I'm using square brackets. The only reason we do that is so that if you just keep using curved parentheses, it just gets confusing a lot faster. So if you make one set of them square, you know what's paired with what, and then the round ones are paired with the round ones. That's the only reason I switched to the square brackets. Distribute the negative sign, so x minus 3 minus I, x minus 3 plus I. Okay, and we need then to do some multiplying. So let's start off with the complicated stuff. Now, once again, we're going to see like the last time, anything that has i's in it should end up canceling away to 0. So my 3x3 grid of mathematical delight, ooh, that got a little exciting. Oh, goodness. I've made better grids in my life. Don't tell anybody about this part. So x minus 3 minus I, x minus 3 plus I, and just keep track of everything. This, there's this, another one of those, there's that, there's that. Then here, let's do a little work in our heads, right? It's going to be negative I to the second. I to the second is the number -1. -1 is just +1. Hey, let's make sure things cancel. Minus ix plus ix. Minus 3I plus 3I. So this x plus 1 gets multiplied by x squared. Minus 3x is minus 6x. 9 and 1 is 10 all together. Okay, now everything is real. No more imaginary stuff. So we can just multiply out. Now, by all means, set up another grid. And actually, let's just set up another grid. We got a trinomial. And then this binomial. So x to the third minus 6x squared plus 10x. Then here, another x squared minus 6x and a 10. All right, I think we're all through then. Let's call this x to the third minus 6x squared plus x squared is going to be a minus 5x squared. And then 10x minus 6x, that's plus 4x, and then a plus 10 on the back. So you're not going to hear me say this is easy, but it is much easier if you organize yourself. First, make sure you have all your roots, set up your factors, distribute the negative, multiply the complicated looking stuff so that it becomes less complicated. One final type of problem you're going to see on that extension practice sheet is, given a polynomial, we're not going to do any analysis of it, so you don't even look at a graph of it. Based on just the degree, so the highest variable exponent, we can make some educated conjectures. So we know some things about the types of roots that we're going to have. Let's start with this first part. State the number of complex zeros. So this includes the imaginary ones and the real ones. Well, according to your fundamental theorem of algebra, there are going to be 4 complex zeros. That's because it's degree 4. Don't make that tougher than it is. Now, possible number of real zeros and imaginary zeros. This is where we're going to now focus on our complex root theorem. The one that says, if I've got one imaginary zero, like 2 plus I, I'm going to have another imaginary 0 of 2 minus I. Those have to come in pairs. So when it comes to imaginary zeros, I guess, well, there could be none of them, but there can't ever be one of them. They have to come in pairs. So 2 is a possibility, but 3 isn't. Because if I have a pair of 2 and then another one, I've got to have a second pair to go together. So of my roots, either 0 of them have i's in it, a pair, so 2 of them have i's in it, or 2 pairs, all 4 have i's in it. Only even-numbered options can occur. So when you are then answering this final question, the number of real zeros, just take, there's going to be 4 altogether. So if there's 4 altogether and none of them are imaginary, all 4 have to be real. If there's 4 altogether and 2 of them are imaginary, well, then the other 2 have to be real. If there's 4 altogether and all 4 are imaginary, then none of them are real. There it is. With this conversation in mind, please do a quick pause. I want you to try the same thing now with this next one. Then unpause, we'll see if we end up in the same spot. So first, ascertain the degree. This is a 5th degree polynomial. So altogether, there's going to be 5 zeros. And when we say complex, we're simply saying, hey, there may be some i's involved, some imaginary numbers. Our complex numbers, so our imaginary ones, our purely imaginaries, they must come in pairs. So there could be none, there could be 2, there could be 4, but that's it. There can't be 6 because we only have 5 roots altogether. So our only options this time are, again, 0 or 2 or 4 imaginary zeros. Now, how many it actually is, we would need to do more investigation for. We're simply listing possibilities. Well, then now it's a subtraction problem. Because if I know there's going to be 5 altogether, and if it's the case where 0 are imaginary, then all 5 have to be real. If there are 5 altogether and 2 of them are imaginary, then the other 3 roots must be real. And if there are 5 altogether and 4 of them are imaginary, well then the other 1 has to be real. So as you're working through this type of problem on your practice, make sure you check your answers as you go, and if something's not matching up and you're not sure why, check in with a neighbor or check in with me.